Hello and welcome everyone to the last lecture of our CUDA programming. So in the previous lecture we saw things related to the dynamic parallelism, right? So we saw how to launch a kernel from within a kernel, and then we saw multiple examples related to it, and then we saw the computational memory aspects related to the dynamic parallelism. And then we started off with multi-GPU programming, and we saw multiple APIs for doing multi-GPU programming. And then we looked into warp coding, that is uh, how to use this underscore underscore all underscore underscore any and underscore ballot and popsy and these functions which are used for warp coding, and we saw examples related to them. And then finally we saw how to do fast atomics using this warp coding functions, and there we ended up there we ended our previous lecture. And yeah, so that was the outline for the previous lecture. For the today's lecture, we are planning to see this multi-dimensional arrays in CUDA, that is how to use the multi-dimensional arrays in CUDA. And for doing that, we'll see three use cases for it, that is three examples for it. So yeah, with this, let's get started. But just before that, let me see if there is any. Okay, so there is no further question, so let us begin. So let us start with our first use case or our first example, which is matrix squaring. So we have already seen this matrix squaring application in context of, I mean, this we have already seen this matrix squaring in uh, computation lectures, right? So in that, during those lectures, we saw how to do matrix squaring. But if you remember, during those lectures, we were using one-dimensional array for representing a matrix, and we were accessing matrix like we're accessing 1D matrix using this formula to access it in a 2D manner. So okay, so essentially we were not using two-dimensional or three-dimensional arrays, or we were just using one-dimensional array for performing matrix, for performing matrix querying. But here we'll see how to use actually 2D matrix, or that is two-dimensional array, for performing matrix querying. So we'll see example for that, but let us briefly recap what we saw in that in those computation lectures, that is how to perform the matrix query. So this is our CPU application for performing the matrix query. So we are, we have this function CPU square, which takes this matrix as input, which is nothing but the one-dimensional array, which represents the two-dimensional matrix, and again the result array, which again represents a two-dimensional matrix. So here matrix contains the input, this matrix pointer, uh, which points to some one-dimensional array, contains that input matrix, where the result is the unsigned pointer, which points to the final, points to the array in which we will store the final result. And the matrix size is the size of the matrix, that is we have 32 cross 32 matrix. And for performing the matrix squaring, what we do is we have this triply nested loops, right? So we go from the I goes from 0 to matrix size, J also goes from 0 to matrix size, similarly K also goes from 0 to matrix size. And what we do is we do this result of Ij equals to matrix of Ik into matrix of Kj. But since if you observe here, since the matrices are, not matrices, but this pointers which points to some array are one-dimensional array, we need to access this matrices which are result and matrix in we have to access this two-dimensional array in one-dimensional way, right? Because these they are pointing to the array, they are pointing to the one-dimensional array. So this is this is okay, but let us, in order to make it more readable to a programmer, let us see how to do it in more better way, that is by accessing it in 2D manner, accessing and declaring it in 2D manner. So yeah, but before that, let us quickly look at this GPU version 2 that we saw in our computation lectures. So here, in order to parallelize this CPU matrix squaring application, what we did in those lectures were that we tried to parallelize this two outer loops, right? That was our goal, that we want to parallelize these two outer loops. And for doing that, what we did is we wrote this kernel, right, which is square. And it was launched with n comma n, that is 30, where n is 32, so 32 blocks and each block having 32 threads, and we are passing this matrix result and n as the arguments there. And what we are doing inside the kernel, so this kernel takes this three things as input, which is passed during the kernel call, and what it do is it calculates the ID using the standard formula that we know. And
232.
sorry, is there a question? Hello. There was some voice from someone's side. If there is any question, then please feel free to unmute and ask. Okay, let me see. Okay, no issues. Okay, if there are no questions, then I'll move further. So yeah, so this is the typical GPU. I mean, this is the matrix squaring application that we parallelized it on GPU. So we parallelized the I and J loop, the outer two loops. And what we did is like, yeah, so we were launching this kernel with n comment, that is 32 blocks, where n is 32. So 32 blocks and each block having 32 threads. And then we were having this standard formula for calculating the ID, and ID will go from 0 to 1023, right? In this case, because n is 32 and n into n is 1024, so ID will go from 0 to 1023. And how I and j are calculated? So I and j will give us the unique tuple. So when ID is 0, II will be 0 and jj will be 0. And when ID is 1, II will be 0, jj will be 1. So 0, 0, 0, 1, 0, 2, and so on until 031, and then 1, 0, 1, 2, 1, 3, and so on till 131, and so on. So we'll get unique tuple for ij, if you remember from our computation lecture. And with this unique tuple of ij, what we do is with this we can eliminate this I and j loop, as we have this unique values of for I and j for each thread. And what we do is we just now have this k loop, and then we perform this regular computation that we were doing here, that is result of ij plus equals to matrix of ik into matrix of kj. Okay, so far good. I mean, so good. So like we can parallelize this application on GPU by eliminating these two outer loops. But the thing is, we can do it even better. That is, instead of writing this, instead of declaring this matrices, which are matrix and result, as one-dimensional array and accessing them as accessing this two-dimensional data structure in one-dimensional way, because they are declared as 1D data structures, right? So instead of accessing them in this way, what we can do is we can actually declare them as a two-dimensional matrices. Here, please note that this matrix and result are just one-dimensional arrays, and since they are 1D, even though we have stored 2D data in it, we need to access them in 1D. This manner, this I into matrix size plus jj. Now, what our requirement is, we want to declare them as a two-dimensional data structure, and we want to access them as a two-dimensional data structure, not like this in 1D manner. We want to actually access them and declare them as two-dimensional data structures. So for doing that, we'll now see the version 3, so GPU version 3. So for doing that, we'll see the code corresponding to it. So this code is splitted across multiple slides. So this is the first slide, and yeah, so let us see how to do this. So we have this matrices A and B declared on CPU. Please note that now this A and B are two-dimensional matrices. So n comma n we are declaring, and similarly A and B are declared as n comma n, n cross n, and then we are declaring this variables block per dim and thread per block, which are of type dim3, and we are passing this value 1 comma 1 and n comma n here. So what it is, what it is doing is, it is specifying that we want grid of dimension 1 comma 1. That is, we just want to launch a kernel with one grid, and inside that grid, that single grid, I want a thread block which has dimension n comma n. So please note that this grid and thread blocks are this grid and thread block are now two-dimensional. So since we are specifying 2-dimension to it, it's now a 2-dimensional grid and 2-dimensional thread block. And grid is just, I mean, there is just one grid because it's 1, 1. For thread block, we have specified it, its size as n, n. So since n is 32, n, n is 1024. So it's one grid and 1024 threads in that grid. Sorry, one thread block and 1024 threads in that thread block. Sorry for that. So, and then what we are doing is we are initializing the value of uh, initializing the matrices A and B. Please note that I have just added comment here, but I mean, I have not added the entire code for the initialization here, but please assume that there was a code or subroutine which initializes the value of A and B. And after this initialization happens, what we are doing is this part is important. We are doing this CUDA mem copy to symbol. So what this CUDA mem copy to symbol does is that it copies values from this mnemonic. So please note that this array, I mean this array variable is nothing but a mnemonic when it comes to C++. So it copies the value from this mnemonic or a symbol, which is A or B, to this DA. Now what is this DA? We'll come to it. It's again a matrix which is declared on GPU, but we'll see what it is in the next slide. So okay, so we are doing this CUDA mem copy to symbol. It copies all the values which are there in this matrix A, which is on CPU, to the DA, which is the matrix on GPU. And how many elements does it copy? That is equals to size, which is n into n. I have not specified size here, but okay, so please consider the size was some variable which was initialized to n into n. But yeah, I have not specified it here, but yeah, it's n into n. And this 0 is, I think it's a default value, I guess. I'm not sure about this 0 one, but okay, I think this is a default value. And this part is important, CUDA mem copy default. So what it says to us is that I'll let compiler to figure out what is this A and what is this A. That is, compiler can figure out, I mean, what is the direction of the data transfer, whether it's from CPU to GPU or GPU to CPU. So it will figure out that, okay, A is on the CPU and DA is on the GPU, so I want to transfer the data from CPU to GPU. So, well, I hope that this is clear, CUDA mem copy to symbol. So we are transferring this data from CPU matrix A to DA, which is the GPU matrix, and similarly here from D, which is CPU matrix, to the GPU matrix. And then what we are doing is we are doing this, we are launching this kernel SQR, and we are passing this block per dim and thread per block, which were declared here and here. And then we are passing this value of n, which is 32, right? And then after doing that, we are doing CUDA mem copy from symbol. That is, we are copying the computed result, which was in dB. We'll see how the computation happens. So we'll copy this value dB, which was there in this matrix dB, to A. Please note that A is this array on CPU. And then we'll finally print the result stored in A, which will be our which will be our final matrix, which contains the multiplication result. And yeah, now let us look into the kernel part. So this is how the kernel will look. Okay, I think I have yeah, I think this should not be sample, but it should be square. Yeah, this part is please consider this name as square instead of sample. But yeah, so let us look into the details of it. So we have this kernel, right? SQR, this one, and which is this. So it was launched with one grid and 1024 threads in it, and threads were thread block was having 2 dimension, and yeah, there were 2 dimension X and Y, and there were 32 threads in 32 threads in each dimension. So yeah, so let us look into this kernel later. First of all, let us see this thing. So if you remember this DA and DB, where I told that they are matrices declared on the GPU. So how we declare it on the GPU? We specify it using this underscore underscore device underscore underscore int, and then DA, of size n cross n. So this will declare a matrix similar to how we did it on CPU here, but on GPU. So now this matrix of size n cross n is on GPU, which is DA. Similarly, we are declaring DB on the GPU of size n cross n. Now this DA and DB are on GPU, and we have also transferred values to it from A and B to DA and DB here on CPU. Now let us come to this kernel part. Now inside this kernel, we need to calculate the unique tuple for I and j, right? So how will we do that? It's simple here because we have this two-dimensional thread block, right? So thread ID x dot x will go from 0 to 32, and thread ID x dot y will go from 0 to 32, because if you see here, x dimension, I mean, there are n threads in x dimension and n threads in y dimension. So thread ID x dot x will go from 0 to 32, where n is 32, and thread ID x dot y will go from 0 to 31, not 0 to 32. Yeah, it will go from 0 to 31. Thread ID x dot x will go from 0 to 31. Thread ID x dot y will go from 0 to 31. And yeah, we'll have the unique combination of j and I. So j will be 0, I will be 0, j will be 0, I will be 1, and so on. J will be 0, I will be 31. And then j will be 1, I will be 0, j will be 1, I will be 1, and so on. J will be 1 and I will be 31. And this will go on until the last row, that is j will be 31, I will be 0, j will be 31, I will be 1, and so on until j will be 31 and I will be 31. So we will have unique pair of I and j, and for each thread. Oops, we'll have unique pair of I and j for each thread, and yeah, after having that unique pair of I and j for each thread, what each thread does is we have this for loop, right? It does this computation, this for loop computation, and in this for loop computation, k goes from 0 to matrix size, and this is important part. Now the way we are accessing the matrix here, which is DA and DB, is in very similar manner to how we do it in CPU, that is in two-dimensional manner, right? So please note that we are doing dB of ij plus equals to dB of ik into dB of kj, which is very, I mean, please note that we are not doing this type of thing, right? I into matrix s plus jj. We are not accessing a one-dimensional matrix, which is one-dimensional data structure in two-dimensional manner, but we are actually accessing a two-dimensional data structure in 2D manner. So that is what is the difference. That is, what we have learned is we have learned how to declare a two-dimensional matrix on GPU and access it in a two-dimensional manner on GPU, and this thing can be generalized to even three-dimensional or higher dimensions. So if you want to do some three-dimensional operations, then what you can do is you can specify this, I mean, you can add more dimensions here. So this DA can have more dimensions. Let us say there was a third dimension of size n, similarly for DB, and you can just calculate the value of ijk accordingly, based on the size of the grids and the thread blocks and so on. And then you can simply do this dB of ijk plus equals to dB of ikj and so on. And yeah, that is the way you can even access three-dimensional matrix on the GPU. And the most important thing here is that we have avoided this complicated formula type of calculations, right? Here, that IA into matrix S plus JJ. Now assume that you are going to even higher dimension, that is 3 dimension, then this formula will only get more complex. So that thing can be avoided by using this, declaring this 2 or 3 dimensional arrays on GPU and then accessing it directly as 2 dimensional or 3 dimensional array. So I hope that this is clear. Let me see if there are any questions. Okay, I think someone has raised the hand. Please feel free to ask the questions if you have any.
Sir, the program what you have discussed right now is simply squaring, or it is like sigmoid function, MAC? It looks like a MAC.
I think it's simply squaring. As far as I've checked, it's just performing the matrix squaring.
Because squaring means simply multiplication. Why you are adding that one on dB? dB of ij is equal to you are adding. So I was wondering, is it like Mac or simply squaring? I'm
No,
confused.
I think it's simply squaring. So one thing I'll do here is that after this lecture ends, I'll upload the code for it in the same Google Sheet that we use, right? I mean, for recordings of the lecture. So these codes I have already tested and ran once, and I'll
Okay.
check the results. So I think they are performing squaring only, as far as I remember from my last check that I made. So yeah, but just in case if I missed something, I'll just upload the code and you can run it on either your own personal machine or Colab or something. So yeah, one point that I forgot to mention for this lecture is that the codes that I am going to discuss in this lecture would be there in that folder, that I mean all codes linked, right? That was there in that sheet. So you won't find these codes on that link that is present on sheet. So I'll explicitly upload all these codes that we are discussing today, and you can run all these codes on either on Colab or sheet and check the results, and even you can modify it and see how uh, how the results vary and so on. Okay, so any other questions apart from this? Just let me- Okay, I think Gokul is saying, could you say the CUDA mem copy from and to symbols? So do you want me to repeat that CUDA mem copy from and to symbol, or okay, let me just briefly recap, I mean do the recap of it. So CUDA mem copy from and to symbol, what it does is it copies the data from provided symbol on CPU to the GPU. So here A is nothing but a mnemonic, right? So name of an array is nothing but a mnemonic. So it will copy the data which is there at present at this address or this mnemonic from here to the whatever location, I mean whatever address is provided here, that is on the GPU. I mean here we are not explicitly specifying whether it is CPU or GPU, because we are using CUDA memcopy default. So what CUDA memcopy default says that I mean it says that okay, I'll let compiler to determine what is the uh, way in which we are transferring the data, I mean whether it's from CPU to GPU or GPU to CPU. So it will figure out that okay, this A is on CPU and DA is on GPU. Similarly, it will in this case it will figure out okay, so this DA is on GPU and A is on CPU, so it will transfer from GPU to CPU. Okay, so that is what is CUDA memcopy default, and this is the source, this is the destination, which both are the mnemonic, I mean both of them are the mnemonics, right? Because they are just the symbols, I mean they are name of the array is just the placeholder, right? In C++. So here DA as well as the A, B, okay, DA, DB, A and B all are the mnemonics. So they just hold, I mean they just hold the addresses, and CUDA memcopy to symbol, CUDA memcopy to symbol, and from symbol will transfer data from stored at this address to this address. And how much data will it transfer? It depends upon this parameter, which is size. So this much data will be transferred from this to this, that is from source to destination. I hope that is clear. Any further questions? Okay, there is some question. Okay, grammar. Is this code we are in this code we are just doing multiplication of A with X, similar to normal C type code. Okay, I'll leave this thing to code itself, right? So I'll upload that code itself, I mean put that code itself in a sheet, and you people can check that by running it on your machine or Colab. Okay, got it. Okay, so I think so far we are clear with this matrix multiplication, and I hope that you are getting flavor of this thing, right? That we are accessing, I mean we are declaring as well as accessing a multi-dimensional array on CUDA here now, as opposed to what we used to do during our computation lectures, right? That we were just declaring it as just one-dimensional matrix, and sorry, one-dimensional array, and where we were accessing that two-dimensional matrix in one-dimensional form. So we are not doing this thing. We are doing something better, which is more readable like this. So I hope that you understood this, and with this, let us move further with our next application. That is our second use case, which is 2D minimum algorithm. So let us understand what is this 2D minimum algorithm. So here we have a window of size 2 cross 2, and what we want to do is we want to go through each window of size 2 cross 2 on the given input matrix. So this is our given input matrix, and we want to go through each and every window of size 2 cross 2, and we want to find minimum value in those windows, and we would like to place that value in the output matrix. So for that, what we do is yeah, we'll go through this window. That is I'm taking this example. So we'll go through this window, which is of size 2 cross 2. We'll find the minimum value in it, which is 2, and we'll place in the output matrix. Then again we'll go to the next window, which is of size 2 cross 2, that is this one, and the minimum value here is 3, so we'll place 3 here, and so on. Next window is this. Here the minimum value is 2, and we'll place 2. Next window is this, and the minimum here is 2, and we'll place here. And if you see, this operation is very similar to the convolution operation that we do in image processing and so on. And but here the window size is fixed. There we can use different size of filters or feature detectors and so on. So yeah, so I hope you are getting this. We have this input matrix. We have a window of size 2 cross 2, and we want to perform the minimum operation on that window size, and we want to place it in the some output matrix. So please note here that the size of the output matrix is smaller than the input matrix, but generally is not. I mean, it is not the case. So the example that we are going to see, we'll see that we are copying this first row and last column as it is in the output matrix. So here I have not shown that. So this first row and last column, which doesn't changes, right, because of the way we are performing the operation, are copied as it is here. And what changes is this middle part, this part of the matrix, and that change is reflected by this matrix, output matrix. So okay, so I hope you got this. What is this 2D minimum algorithm? And yeah, this 2D operations, like this 2D minimum algorithms, are found in many fundamental algorithms like interpolation and convolution operation and filtering and so on. And they are also applied in several real world scenarios like seismic processing, weather simulation, and image processing. So this is a good example of how to process a multi-dimensional array either on CPU or GPU. So we'll look the code for both of them. Okay, so let us first formally define this 2D minimum algorithm. So yeah, so that this is the formal way of specifying it. So each output element is the minimum of the input element within the window, and here the window is of size 2 cross 2. So as in terms of formula, it is like this. So we want to go through I minus 1j, I minus 1 j plus 1, ij, and ij plus 1, and want to place the output value in some output matrix, which is O. So A is the input matrix, O is the output matrix, and O of ij is the place where we are placing the final output value. So coming to this figure, it's like this. Just let me, yeah. So for this value, we'll go to, we'll see this value, this value, this value, and we'll find minimum out of all this, and we'll place here. So that is what we are doing here. For ij, we are going to I minus 1j, I minus 1 j plus 1, and ij plus 1, and we are placing in O of ij. And okay, rows are going from 0 to n minus 1, and columns are going from 0 to m minus 1. That is, we have m cross n matrix. So this is not a square matrix, and it cannot be a square matrix. It can be a rectangular matrix also. And considering that in mind, and considering that the computation boundaries remains intact, and also assuming that the initial values are values in A are initialized using some random function, we want to write a CPU code corresponding to this 2D minimum algorithm. How can we write a CPU code corresponding to this 2D minimum algorithm? Quickly, can anyone specify how we can do this on CPU? It won't be that difficult, right? Because on CPU it's straightforward. How can we write the code for 2D minimum algorithm on CPU? I'll probably wait here for your responses. Okay, Gokul has some question, but sir, first row and last row values are different from output matrix. I probably missed it. I mean, probably I missed something here. But what I was trying to say here is that since for the first row we don't have I minus 1, and for the last column we don't have j plus 1. We won't be able to do 2D minimum operation for them, right? For this row, this first row, we don't have I minus 1, right? And for this column, we don't have j plus 1, right? So we won't be able to do 2D minimum operation for this row and this column. So they'll be copied as it is here and here. So final output matrix, how would it look? So it would have this row and this column copied as it is here and here. Apart from this part, this 3 cross 3 matrix here, which is shown here, will become like this. It will become like this. That is what I was trying to suggest you when I was saying that first row and last column remains intact. If there is any further confusion, then you can okay, no problem. So please think about how we'll just write the simple CPU code corresponding to this 2D minimum algorithm. It would be really very quick. I mean, there is nothing much going on here. I'll probably wait for a few seconds here for you people to try. There is some response for CPU code. We just walk through array and use YJ formula. Yeah, I mean that's correct. So Varun has given some suggestion. Loop for each element of output and compute using formula. Yeah, that is correct. So this is what I want. So output array size and plus 1.1. Yes. So this is good. I mean, this is what I want. So there is nothing much going on here when it comes to CPU 2D minimum algorithm. Let us see how to do it on CPU. Then we'll come to the GPU part. So here I have written two functions. One is init and one is compute. So if you remember, we want to initialize the value of a to all the random values, right? So in init function, I have declared two arrays. One is grid and one is previous grid. So if you see here, a is the input array and o is the output array. So in order to simulate this, what I'm doing is I'm using input array is previous grid and output array is grid. So our previous grid will contain the input values, and grid will, after the execution of the algorithm, this 2D minimum algorithm, this grid will contain the final results that we want. And how we are performing the initialization? It's very simple. We are just running two nested loops, and we are calculating some random values in rand function on C, and then we are initializing both grid and previous grid using those values. So initially grid and previous grid both are initialized to our input our input matrix. So both OA and A contains the initial input that we wanted, right, which was initialized using random. And now inside compute function, what we are doing is we are passing this grid and previous grid which were initialized here, and what we are doing is that we'll have two nested loops here again. And first loop, which is outer loop, which goes over all the rows of that matrix, will go from 1. It will not go from 0. Please note that it will not go from 0 because first row and last column are ignored. So rows will start from 1 and go till n minus 1, and columns will start from 0 and will go until n minus 2. So please note that it's less than symbol. So n-1 is meaning that it will go from 0 to n-2, and I will go from 1 to n-1. So first one, last column are ignored, and the way we are calculating this, this value of this, each output value which is stored in the output matrix, which is grade of ij, is using the this our standard formula, this one. So yeah, so this is the same, this thing, this entire thing is same as this one. So I hope this CPU code is clear. We are not doing much here. We are just using this formula, and we are using the doubly nested loops and using this formula to get the final result. Okay, so this is fine. Now we want to do the same thing. We want to perform this 2D minimum. We want to implement this 2D minimum algorithm on GPU, and for this implementation, what we want is what our requirement is. We want to eliminate all the loops. That is, we don't want any doubly nested loops here. We just want one thread to operate on each data item, which is the one output element, and compute the final result without using any loops. So that is our requirement. I request you people to try this out first before I present that GPU code for this 2D minimum algorithm, and it will be a good exercise for you people. And one hint that I would like to give you here is that the code is very similar to this matrix squaring code. But here in matrix squaring, we were having triply nested loops, and we were parallelizing two loops here, and third loop was kept as it is. But in this case, we are parallelizing both the loops, and there won't be any loop inside the kernel. So I request each and every one of you to try thinking about how we can write the GPU code corresponding to this 2D minimum algorithm, and then we'll discuss. Meanwhile, let me see if there is. At the end, we just walk through first one, last column, and then add. Okay. So Gokul is telling call a kernel within kernel. For what you want to call a kernel within kernel? Gokul, can you clarify? Meanwhile, I'll go to slides so that others can see this code and try to parallelize this on the GPU. Go back to the chat. Okay, for the GPU code, you want to call a kernel from within a kernel. Can you elaborate on that? How will you do that? Well, in this case, this is not a irregular application. First of all, let me clarify this thing. So I specified this thing right in the previous lecture when the loop bounds are not known. That is, we don't know how much. For either of the loop, if we are unsure about how much iterations it is taking, then in that case, it's a good point to use the dynamic parallelism. But when the loop bounds are already known, here we know that n is 32, right? In this case, loop bounds are already known for both the loops. That is, we know how many times both the loops will run. In that case, we can use dynamic parallelism. That is correct that we can use it, but we can also implement this entire thing without using dynamic parallelism is what I'm suggesting. And when there is option of going for static parallelism instead of dynamic parallelism, we should go for static parallelism since there are lesser overheads. That we saw in the previous lecture, right? So yeah, but in case you are interested in parallelizing it using dynamic parallelism, then please feel free to do that. We can discuss this even for the dynamic parallelism case. Okay, I'll wait for a few more seconds and then we'll discuss the GPU code for it. just in case anyone wants to try this, try parallelizing this on GPU. There is some response. Ice thread ID x.express. Okay, this is the standard formula. J is equals to I equals to okay. Okay, I think this is correct. I did something like this only. I think this approach is correct. Let us, okay. Well, this is good that at least some of you are trying. Okay, there is one doubt, sir. In CPU, it will be sequential, so we'll be able to compare with updated values in previous rows. But what about if it could happen in any other? Okay, you are talking about GPU, right? This is a valid question, Gokul, but if you see here, we are using two separate arrays for input and output. So reading and writing are separated, if you see here. So we are reading from one array or one matrix, and then we are writing to another matrix. Data race or issue that you are pointing out will only happen when we are reading. Some thread is reading as well as the other thread is, some thread is writing and other thread is reading from that memory location, which will not happen here since we have to separate grids, which is grid and previous grid. Okay, any further questions? Yeah, so I think this approach given by Varun is probably it's correct one, and probably I also thought the same thing. So yeah, let us look into it. So let us look into how to implement this 2D minimum algorithm on GPU. So again, if you see, we are passing this grid and previous grid, which was initialized using on the CPU, and then we are initializing, well, n is 32, please note that n is 32, and then we are declaring this block per dim and thread block as 1 comma 1 and n comma n, that is one thread block, and that thread block has n comma n threads, that is 32 into 32 threads, and grid and thread block are two-dimensional. Size here, which I missed in the previous example, in the previous example I missed adding that this line, which is the declaration of size. So size is declared as n into n into size of it, and then we are doing this CUDA mem copy to symbol, that is we are copying the data from grid to the D grid and previous grid to the D previous grid. So D grid and D previous grid are declared on the GPU, and we'll see in the next slide how they are declared in the similar manner that we saw in that matrix squaring application, right? And then the amount of data that we want to transfer from grid to D grid and previous grid to D previous grid is equal to size that we declared here. And then we are specifying that CUDA mem copy default, that is we are specifying that by default it can compiler by default decide which direction the data transfer is. And then we are launching this kernel sample with this parameters, that is block per grid and thread per block, and we are passing this value n, that is 32. And then we are doing CUDA mem copy from symbol, that is we are transferring the computed value back from D grid to grid. So D grid will have final result on GPU, which is now transferred to CPU, which will be stored in grid. And grid is the array on CPU. Please note that grid is the array meaning this two-dimensional matrix on CPU. This grid is the two-dimensional matrix on CPU. Just a moment. So yeah. Okay, so yeah, let us come to this this kernel part. So this kernel which is sample, which was here, is this one, and we have seen this launching part. Now let us come to this part, which is the declaration of this D grid and previous grid. So D grid and D previous grid are the two-dimensional matrix similar to this grid and previous grid declared on CPU. So, but this D grid and D previous grid are declared on the GPU, which are of size n cross n, similar to what we have on the CPU. And then, as Varun wrote, I mean that kernel part. This kernel is very similar to that part. So, in this kernel, what we are doing is we have this input matrix size, that is 32, which has the value 32, and we are calculating the value of I and j. And please note that this the way we are calculating this, way we are calculating the value of I and j. What will happen is we will get the unique tuple for I and j. So yeah, I hope that this is clear. The way we were having in that matrix squaring application, that we will get the unique tuple for the I and j, and after getting that unique tuple for each thread, so for each thread we'll have that unique value of I and j. And if that is the case, we can completely eliminate the loop that we saw here, right, in the CPU code. We can completely eliminate this loop, because now each thread has the unique value of I and j. Okay, so but one thing that you should keep note of here is that we need to specify this if condition here. Otherwise, it might happen that there might be a sag fault on GPU, because for the first row, which has I equals to 0, if you do I minus 1, then it will access the row minus 1, which is not there, right? Minus 1 row is not there, so it will lead to sag fault. And j should be less than n minus 1, because for the last row we don't have j plus 1, right? Because for the last row, j plus 1 will lead to sag fault. So this condition is important. I should be greater than 0 and j should be less than n minus 1. And if this condition is being satisfied by any particular thread, what we'll do is we'll calculate the minimum using our standard formula. And please note that here again we are using that we are using the two-dimensional matrix for performing the operation on 2D, for performing the 2D operation. So we are not using one-dimensional array and accessing it in two-dimensional array. We are actually declaring a two-dimensional array on GPU and accessing it in 2D manner. And yeah, so the final answer will be in D grid, and this D grid will be transferred from GPU to CPU, and it will be stored inside grid. So I hope that this is clear. Then you can print this grid, and you can get this final result that we were expecting here. So I hope that this is clear. This GPU code is clear for this 2D minimum algorithm. This kernel is clear. So okay, any questions up till this point? Any questions up for 2D minimum algorithm or matrix squaring application, or any of either of two? Okay, I'm assuming that there are no questions. In that case, let us look into the last application for today, which is stencil computation. Oh, sorry, which is stencil computation. Yeah, so let us look into this stencil computation, and this is very similar to this 2D minimum algorithm. So in this stencil computation, our formula is slightly different compared to 2D minimum algorithm, but there is a one small catch here that we will see later during this example of stencil computation, and we'll tweak this stencil computation a bit in order to get a more involved scenario here. So okay, so first of all, let us start with this problem itself. To design and implement a stencil computation wherein each iteration cells compute their values using neighboring ones, and the way they calculate the value is according to this formula. So each cell, it looks into the two cells that are above it, so I minus 1j and I minus 1j plus 1. So immediate above neighbor and the neighbor which is above and in diagonal to it. So these two neighbors are being looked by a particular value, and what it does is it adds the value of these two neighbors into it into the cell into its cell. So This is the functionality that we want to implement. Again, the rows go from 0 to n minus 1 and columns go from 0 to m minus 1. And as we saw in the 2D minimum operation, the computation boundaries remains intact. And yeah, for this application, we want to initialize all the values of the input matrix, which is A, to zeros. And yeah, the program that we want to write should run for 10 iterations. That is, if you see in 2D minimum algorithm, we just ran it for one iteration. So we are taking that input matrix, we are computing the minimum in each window, and we are putting it in an output matrix. But here we want to do it 10 times. So after first iteration, all the cells will have their values computed. Computed using this formula once. And after 10 iterations, their values will be computed 10 times using this formula. So I hope this is clear. The idea is clear. What is the problem that we are trying to address is clear. And pictorially, it looks like this. So for for this value, that is, if you want to compute this value in output matrix, this is the output matrix. If you want to compute this value in the output matrix, we'll take these three values in the input matrix: this one, and this one. So please note that if this is the I comma j cell, then this is the I comma j cell of the input matrix, I minus 1 j cell in the input matrix, and I minus 1 j plus 1 cell in the input matrix. So this is exactly what it is, right? This formula. And pictorially it is shown like this. So I hope the problem statement is clear, and would like to implement this functionality, and its implementation is quite simple. This basic implementation that I'm talking about is quite simple. So let us come to CPU part first. So for the CPU part, what we'll do is we'll have this outermost loop, which will run for the 10 iterations, right? That we wanted to have 10 iterations in the outer loop, right? So if you remember here that we are having this thing, right, that we should run it for 10 iterations. So the outermost the outermost loop goes from 0 to 9, that is for the 10 iterations, that is ITR will go from 0 to 9. And then what we are doing is we'll perform this stencil computation, that is will go from 1 to n 1 to n minus 1. Please note that we'll ignore the 0th row here, because for the 0th row, again we don't have I minus 1, and for the last column, we don't have j plus 1. So again, first row and 0th row, or the first row in this case, and the last column are ignored. So we'll start from I equals to 1. So from I equals to 1 to n minus 1, and from j equals to 0 to n minus 2, we'll do this thing, which is nothing but our formula that we saw in those in that problem statement slide. And what we are doing, please note that we are using two different matrices for input and output. So as you can see here, input matrix is different and output matrix is different. So input matrix is previous stencil and output matrix is stencil. And after doing this for one single iteration, what we are doing is we are copying the data back from this computed data back, which is stored in stencil, to previous stencil for the next iteration, because for the next iteration, whatever value that we have computed in this current iteration will become the input for the next iteration, right? So let's say in iteration 0, stencil, in iteration 0, the value of stencil, each value in this stencil matrix will be computed using this formula, right? And for this iteration, this not for this iteration, but this previous stencil was having the input values, right? That we should use for computing the output values, which are placed in this stencil matrix. But now when we move to the next iteration, we need to place this computed output into this which is there in this stencil matrix to the previous stencil, so that it can serve as an input for the next iteration. So next iteration will again take the output of the previous iteration and will compute the output for the next iteration, and this will go on. So I hope you are getting why we'll need this one. It is copying the data back from stencil to previous stencil. So okay, so this is a simple CPU code for stencil computation. Okay, well, now I'll ask you people to write the GPU code for this. Again, it's quite simple after seeing that two examples, but there is a small twist that I'll add to it later. But yeah, just try writing a GPU code corresponding to the CPU code, and yeah, probably paste your answers in chat, or you can even unmute yourself and say. Okay, I'll switch back to the slides. I'll wait probably for a few seconds for you people to try out writing this GPU code corresponding to the CPU code. Okay, there are some responses. Naive is 10 kernel launches and CUDA mem copy after each kernel launch to use result from previous kernel launch into the next kernel. Code will be similar to previous example. Yes, that is exactly what I wanted, because yeah, that is what I've done. But yeah, let us see. The conditions, stencil formula, sync thread, copy line. For what do you need sync thread? Gokul here. For sync, what I mean, why are you using sync thread here? Again, I mean, there is no data race or something happening here that you need sync thread, right? Okay, anyways, so let us quickly look into the GPU code, and then I'll talk about its slight different variation of the stencil computation. So again, GPU code is very similar, as someone pointed out, that will use 10 iteration, and this is quite an that's quite naive implementation. So we are using 10 iteration, and in each iteration we are using this, doing this kernel launch, and again there is one grid and 32 into 32, that is n into n threads in a thread block. Sorry, one thread block, and that thread block is having n into n threads, that is 32 into 32 threads. Size is 32 into 32, which is 1024, and then we are copying the data from stencil to d-stencil and previous stencil to d-previous stencil, and then we are launching this kernel during each iteration, and then copying the data back from d-stencil to previous stencil. Please note, this is important, that we need to copy data from d-stencil to previous stencil, as we did in CPU code here, and d-stencil to stencil. And kernel is also similar, like as we saw in that 2D minimum algorithm, that what we'll do is we'll have this d stencil and d previous stencil declared as two-dimensional matrix, that is of size n cross n on GPU using underscore underscore device, and we'll see this. We'll have this global. We'll have this kernel sample, which is declared as underscore underscore global. And if you see, this part is very similar to the 2D minimum algorithm. We are calculating the unique value of I and j for each thread. That is, each thread will have unique tuple of ij, and then same condition which we saw in the 2D minimum algorithm that will apply here. That is to avoid the computation of first row and the last column, and then this formula is very similar to what we saw in that problem statement slide of the stencil computation. Okay, so far it was easy, right? Because there is no much thing involved here. That is, we are just doing the things that we have already seen in the 2D minimum algorithm. Now, this was the original stencil computation, right? That we want to do this computation. Now, I'm adding a slight restriction to this, that the updates should happen in place inside the input matrix itself. That is, if you remember here, we are using two separate matrices, right? This was the input matrix, and we are reading these three values and writing it to output matrix. But now my requirement is different. I don't want to use, I don't want extra space, I don't want to waste extra space for the output matrix. what I want to do is I want to just keep this input matrix as it is and want to do this stencil computation, calculate the values and store results in this input matrix itself. I don't want to declare the output matrix and do calculation and then store the value in output matrix and so on. So I just don't want to do I just don't want to use any extra space. I just want to do the computation in this input matrix itself, that is the stencil computation. So that is the extra requirement that I'm placing here, that the update should happen in place inside the input matrix itself. That is, you are not allowed to use any extra space, either for doing the intermediate computation or for storing the final results. Now, if this is the problem, if this is the question, then how will you write the code for performing this stencil computation? Please think about it. I'll probably wait for a few seconds. Or let us first discuss the CPU code for it. Then I'll probably ask you people to write the GPU code, because CPU code is quite simple, right? We'll have I going from 0 to 10. That is, sorry, ITR going from 0 to 9. That is, from 0 to 9, and then I going from n minus 1 to 1. That is, we are going through each row from bottom up. That is from n minus 1 till 1. And please note that we are ignoring the 0th row because of that restriction of I minus 1. And then j is going from 0 to n minus 2. Please note that this is less than, so it is going from 0 to n minus 2. And then we are using this formula. So on CPU it is okay, we can use this code and it will give the correct result. Now again, I'll come to my question, that if I want to do this thing on GPU, I want to do this in place and stencil computation, on GPU, then how can I do it? I want you people to think about it and share your approaches in chat, or either, you can also unmute yourself and say what you think about it. Meanwhile, let me see if there are. We don't want values to be copied to previous stencil while its value may be used by some function. We don't want the values to be copied to previous stencil while its value may be used by some function. But okay, Gokul, in that case, we are just using separate outcome matrix, so that was not the issue. Probably the issue that you are pointing out might be relevant to this case where we are doing in place updates. Yeah, but please think about this. Meanwhile, I'll look into the question. I guess if you use mem copy, then no issues. For doing input matrix itself, could we use dynamic matrix? Okay, I have not thought about it, but I think you can do it using dynamic parallelism. Well, anything that you can do statically, you can do dynamically, I guess. So that won't be the issue. But my suggestion is, please first try doing it statically, because dynamics have, dynamic parallelism have its own overhead. So yeah, so. Using atomic head. Good. So I think you people are getting the crux of it, that if we do in place computation, that then we might see some data race in the code that we were using here, right? If we use this earlier code, then we might encounter some data race. So this is the important observation, actually, that if we do in place stencil computation, then there might be some data race, and we need to use some atomics, or we need to do computation in slightly different manner, so that we can avoid this data race. It might be using atomics or something else, or even we can use sync threads or something. Yeah, any suggestions by anyone else? Or else probably I'll move forward then. There are no suggestions then. Okay, I think let us move ahead. Okay, so yeah, this is our problem. That is, we want to perform stencil computation in place, and let us try to understand how can we do it on GPU. So on GPU, what will be the issue? So the issue is this, that whenever a particular thread which is working on this cell is calculating its value from by adding this to value and placing the added value, I mean adding the, sorry, not adding, but whenever a particular thread is performing operation on this cell by adding this, this and this value, and whenever a particular thread is performing operation on this cell by adding this, this and this value and placing it here and here, that is, they are writing, the thread that is working on this cell and this cell are writing their values in this their respective cell, that is here and here. What can happen is that another thread which is working on this cell can read the value from here and here and can write here. So the crucial observation here is that the value from this cell and this cell are being read as well as written at the same time by the multiple threads. And if that is the case, then we know that what has happened, which is I mean the data race has occurred right here, and this will occur everywhere. I mean it will occur across the entire matrix across different rows. So it can happen that whenever some thread is writing here, the other threads are writing, I mean some thread is reading value which is working on here from here and here, other threads might be writing on this two cells. So it can occur across entire matrix. So I have just shown one example here, but it can occur across the entire matrix or entire stencil. So okay, so how can we mitigate this data race is the question. So one way that I thought is to do the computation in slightly different manner. So I haven't explored the options of atomics and sync threads that you were suggesting, but that can be a good exercise to try. So the way that I thought of doing it is that since the data race is across the threads of the different rows, that is the threads that are working on this row, and if the threads that are working on this row, two different rows, that is on this row and this row, if they work together, then it can lead to data race. But the threads of same row can work together. This won't lead to any data race. So what I was trying to suggest is this, that if the threads which are working on this row, that is, they are calculating the value from this and this, this and this, and so on. If they work together, then there is no issue because they are reading the values which are there in their in the row which is just above them, right? So in that case, there won't be any data race. So what can be done is that let the execution pattern be this. So once the row which is at the bottom finishes its execution, that is, threads which are working on the row which is at the bottom most is has finished its execution, then only the threads which will work on the row which is above it starts their execution. So we can write the code in such a manner. So first this should execute, then this should execute. So I hope you are getting it, that threads will first calculate this value, this one, for this row, and then they'll calculate for this row. So yeah, it will hamper our performance. That is, we have reduced the amount of parallelism that we'll see with the example, that parallelism has reduced. But correctness wise, we are good, right? Because this will give us the correct results, and there won't be any data race, is what I'm trying to suggest. So let us quickly look into the code for it, but let me see if there are any questions before that. If we just use atomic add a1 comma a0, sorry, a1 comma 0 might get updated after a2 comma 0. If you use just atomic add a1 comma 0, might get updated before a2 comma 0. Yeah, I think using atomics is a good option, but please note that whenever you are using atomics, make sure that not everything is serial. So what I'm trying to say is that please try to write the code using atomics in such a manner that I mean such a manner that not at least some parallelism is there. It should not happen that everything is happening serially, as we saw in the case of that summation operation, right? That we eliminated the loop in that case, but still, due to atomic, everything was happening serially. So in this example, we'll see that there is some parallelism still there, that is rows are, I mean, values of the row are computed parallel, but across the row it's serial. So I hope, sir, is there any way to pass the value to the other thread local variable? Okay, is there a way to pass value to other threads local variable? I think you can do that, but for that you need to have a common memory location. That is, you can declare some variable globally, and what you can do is one thread from its local value will place its local value in that global variable, and then another thread will read that value which is placed in that global variable. I hope that was clear, that there is a way to pass the value to other threads local variable. We can do that using that same global memory. We can exploit global memory. That is what I was trying to say. Before we update each cell, we could compute the value and send it to other threads. Okay, I think this might be doable, but Gokul, I think you need to be more concrete here. That is, you need to suggest how will you do it. So you need to write, I mean, you at least need to write some pseudocode or something corresponding to this, so that we can have at least some idea related to that. That the thread will then look to see its value is there. If its local variable holds value, it will use that, else it will use the value of cells above. Yeah, looks good. But how will you implement all this is what I am suggesting. You need to look into implementation aspects. I think this should work. But I think that code will be slightly complicated. But yeah, sure. I mean, you can try this one. Well, so let us quickly look into this in-place stencil computation code. I mean, code corresponding to this in-place stencil computation. So yeah, the way I have done is that again sizes n into size of int, that is 1024 into size of int. Then ITR is there, which goes from 0 to 9, that is we have 10 iterations. Now what we are doing is we are copying the initial stencil. So please note that now we can't use that d previous stencil or previous stencil, that is we can't use the extra space. So what I'm doing is I'm copying this stencil that is there on CPU to GPU, it is d stencil, and then for each row I'm launching a kernel. So now please note that I have apart from that this iteration loop, I have one more loop on the CPU which goes from n-1 to 1, and first row is discarded because it's I mean because of the time -1 issue. So I will go from n-1 to 1, and what we'll do is we'll work on row by, I mean we'll work from one row to another row. So we'll go from bottommost row, we'll work on that, that is we'll calculate its value, and then we'll go to the one row above it, and then the another row which is above it, and so on till we reach the first row. So for a particular iteration, what we'll do is we'll copy the current row from stencil to d stencil. Then what we'll do is we'll launch the kernel, and during the launch, apart from passing the size of the matrix, that is n, which is 32, we'll also pass the row number, that is on which row currently we are operating, that is I value, right? And then after performing the operation on that row, we'll copy that row back from d stencil to stencil. So I hope you are getting the way we are doing the computation. And then after the entire calculation is finished, that is for a particular iteration, we copy the d stencil back to the stencil. And now let us look into the kernel of this in-place stencil computation. So please note that we are now just launching the kernel with n threads, because we are just working on one particular row, and that number of cells in one particular row is just n, which is 32. And yeah, n and I are the arguments that are passed to it, and we have d stencil, which is of n cross n, which is declared on the GPU. And yeah, so this sample is the name of the kernel, which is declared using __ global, and matrix size is 32. I is the current row on which this kernel is working. And now we just need to calculate the value of GA, right? Because now we are just working on one row, and for that one row we have just 32 threads, and We just need ID, unique IDs from 0 to 30, 0 to 31 for each cell of that row. And once we get this ID, we already have the row number, and based on the row number and the ID, that is the column, column in that particular row on which that particular thread will work, what will happen is based on the ID of the column and the row on which currently this kernel is working, we'll calculate the we'll not calculate it, but we'll calculate the we'll compute the particular or we'll compute the particular value of the d stencil, that is d stencil of ij, using the standard formula. So okay, so I hope you are getting this, that this kernel is launched n-1 times in each iteration. That is, we are doing computation for each row one at a time, in order to avoid this data race that we saw here. So in order to avoid the data race, we are doing row by row computation, and that is done using this thing. That is, we are copying a row from CPU to GPU, then doing operation on it, and then copying back from GPU to CPU. And this is the way we compute it. And if there are any questions, I'll take up those now. But let me see if there is. Yeah, so this was the last slide that I wanted to present, and if there are any questions, then please feel free to ask them. Yeah, any questions on any of the three examples that we saw today?
Yeah, one quick question.
Yes.
What will be faster if we do it the second way relative to if we do it using copy and then parallelize? Because although we are copying, but we get much more parallelization in that case.
Yes, so this is a good question actually. So I think the first way is better, because in that case we have very large amount of parallelization, right? So in that case we are parallelizing both the loops, and I feel that that first way is much faster. Although I haven't timed that thing for the large inputs, so I've run them on small inputs, but for the small inputs we just don't get the exact. We just don't know which is faster for the small inputs. So for large inputs, I haven't tested, but I feel that first one is will be definitely faster, because we have very large amount of parallelism here. That is, we are parallelizing both the loops. Even though we are, there is a disadvantage there, that we are using more space, right? But as a trade-off, we are using more space, but we are getting more speed up. And in the second case, the advantage is that we are saving the space, but the time taken will be more. So yeah, it again comes to trade-off. And coming to your answer, I feel that the first one will be faster. Yeah, so that's my answer. So okay, there is one question from Gokul. Sir, would atomic style implementation be slower than this row-wise kernel call? Okay, well, it depends upon how you are implementing this atomic style implementation. So uh, if somehow if you are able to implement this atomic style implementation in such a way that you are able to get more parallelism than just for, here the amount of parallelism is restricted to that single row, right? So if somehow if you can achieve more parallelism than using this atomic approach, then then n, because here the parallelism is restricted to n. If you can get more parallelism than n, then I think that it should work better. But you need to think about how will you do that. So I haven't thought about implementing this one, that is simple stencil computation using atomics, but that will be a very good exercise for me as well as you to see how can we implement this using atomics. Yeah, any further questions? And I mean, when I say implement using atomics, I mean that uh, without hampering the parallelism. So parallelism is our key goal here, right? That we want to extract more and more parallelism, even though we are using atomics. Okay, any further questions?